This is Abhijit Bhave. I am a student in Boston BU METCS 767, the machine learning program. And this presentation is for me to demonstrate my term project for machine learning and neural networks. So let me get right into it. The topic I chose for my term project was actually to deal with wine quality. What I'm doing is I'm actually leveraging a data set from University of California, Irvine. The data set is basically two CSV files, and I could use either one of them. One is a larger file than the other one. Basically, if you see here, there are two files called wine quality red and wine quality white, which I assume are about red wine and white wine. And both these files have 13 parameters, 12 parameters actually, I'm sorry. Of these 12 parameters, 11 are input features and one is output. Input features are basically things like, what is the fixed acidity in the wine, what is the volatile acidity, citric acid, residual sugar, chlorides, free sulfur dioxide, so on and so forth. And what they've done is they've basically come up with an integer or a floating number for all of these parameters based on how much, for example, how much residual sugar is there in the wine, and they've calculated that based on a sample, and they've included that in the data set. And then what they've done is, based on some algorithm or some rules that they've used, they've basically figured out that for this combination of these said 11 parameters, what would be the quality of the wine. So if you look at this data set here, for the first wine, which has these 11 parameters, they are estimating that the wine would be of quality 5, and the range of quality is between 1 to 10, 1 being the lowest, 10 being the highest. So what I am doing is I'm leveraging this data set, for example, this red wine data set, which is around 1599 rows, I believe. Yep. So 1599 rows. And I'm splitting that data set into 70% and 30%. And I'm using the 70% data set for training, and I'm using the 30%. So training as in to train my neural network to go through this data and figure out how to quantify wines or how to quantify the quality of wines based on these 11 parameters. And then once the model is trained, I am using that trained model to test on 30% of this data set and figure out what the accuracy looks like. Okay, so let's jump right into it. What I'm doing, I have two Python files. So the Python was the tool of choice, and then within Python, I've basically used pandas and NumPy to deal with the data. And then for the modeling piece, I've basically leveraged again Python and NumPy, Python as the language of choice, and then I'm using NumPy and pandas for typical data manipulation, and then TensorFlow as the framework for machine learning and model training, model testing, all of it. And then there is there's this library called sklearn from Scikit, and it basically just is so easy to split data into train and test using this library. So that's the library I'm using. So before we jump into TensorFlow and the actual machine learning, what I'm doing is I've written a Python basically program to pre-process data, and in my TensorFlow model, I'm actually I learned this a little late, but I'm actually trying to run this program with pre-processed data and without pre-processed data. And in this specific case, I'm actually getting much better results without pre-processing the data. But all the theory out there suggests that processing or pre-processing data is a good thing to do. So I did do that first, and then I realized that unpreprocessed data is producing better results for me. So I'll demonstrate both, but I am going to continue to research into why that happened. So this is basically the program where I'm pre-processing data. As you can see, there are two functions basically here that are important. And what I'm doing there is in the first function, I'm normalizing data. So basically I'm looking at the entire data chunk, and I'm trying to make sure that, the mean of the data for every column is close to 0 and standard deviation is close to 1, so that basically normalizing the data so that it's all in the same scale. And then the second thing I'm doing is I'm basically taking the normalized data and I'm making sure that there are no outliers. What I mean by that is that the data falls within a particular range. We don't have like 100, and out of the 1599 rows, we do not have like 1550 rows that are between 0 and 1, and then like 49 rows that are in 300s and 400s, right? Because that would totally skew the data. So if that is the case, I'm basically bringing them back into a similar scale. So again, I'm just scaling this data into one dimension so that all the data points can be plotted across a similar graph, and there are not a lot of skews around data. So that's all I'm doing here to pre-process data. Very basic stuff. I'm basically reading the data, and here I have a flag. So you can either do this on the red wine data set or the white wine data set, and you just set a flag and pick up your input data set. Then figure out what the columns are, normalize that data, remove any outliers, and then once that is done, what I'm doing is I'm basically just adding bins to the data. So my bins are 3, 5, 8. So basically anything that's 8 or above is a wine of great quality. Anything that's is below 8 is good or poor. So those are the only two bins that I've created, and here I'm labeling that data. So we have a numerical label here, and then I'm adding a text-based label here as well, and then I'm basically saving that data as wine data pre-processed. So if I run this file now, what you will see is there. It should not output anything. It should just create a new file when it's done, and that it's done. And then wine data pre-process. This is the CSV, and here you can see, this is the normalized data where the outliers have been removed. This is the quality of the wine that it was. So here it was a 5, and you'll see it's still a 5. And then I've added the label basically. So if you compare row 75, it's 4 and poor. And here on the row 75 it is 4, and now it is 4 and poor basically. So that's what I'm doing in data pre-processing. Once this data is pre-processed, then I'm basically getting into TensorFlow. And again, I do need to remove this import OS because I'm not using it. I was originally using it to test whether the file is still there or not, but then not something that this program needs to deal with. So what I'm doing here is, again, I've basically set a flag that is right now using normalized data, and when I run this without using data that's normalized, I'll comment this flag out and set this flag. So that will make sure that the model is running without data that is normalized or fixed for outliers, right? And then this is exactly what it's doing. So if it is, if it basically prints whether the program is running with normalized data or not. And then if it is running with normalized data, then I have to make sure that I take care of the quality label, which is, the poor or good that we added in the pre-processed data. If I'm not doing that, then we don't really need to take care of this. We just have to convert this, right? So what I'm doing is I'm actually just taking the wine label, and then I'm converting it. And similarly, actually I need to change this to, okay, I'll do that. But similarly, if it is not pre-processed, or if it is pre-processed data, then I'm taking the wine quality column, and then I'm converting it to good if it is if the item is good, and if it is poor, then I'm converting it to 0 if it is good and 1 if it is false. And similarly, if it is not pre-processed data, then I'm converting it to 0 if the quality label is 7 or higher or greater than 7, and converting it to 1 if it is not, right? And the reason why I'm doing this is just to create a binary matrix. And again, I'm going to create a matrix out of this. So I don't want too many numbers out there, right? It's just going to be binary that this wine is good or bad, and that's about it. Then what I do is I basically create a 2 by 2 matrix, and again, like I said, what I'm doing here is if the wine is good, then the output would be 1 comma 0. If it's bad, it's 0 comma 1. So basically helps determine into a 2 by 2 matrix as to why um, whether the wine is good or bad. And the reason to do that is because my y tensor, which is my output, is going to be a 2 by 2 matrix, right? Then, like I said earlier, I'm using this train test split function to actually split my data. My test size is going to be 30% of my data, and then that's going to be x train x test and y train y test, and x is again the input, y is the output. So this is the input for training, this is the output for training, which means these are the 11 features that will be used for training, and for each row there will be a output here, and then this is same for test, right? This is the x test and y test. So I'm basically printing the size of either one of them, because x train and y train are going to have the same size. Similarly for x test and y test, and I'm basically printing what is my size of training data versus testing data. This is just to make sure that we have that 30% split, and that's about it. Then I'm setting some parameters here for my model. So I'm setting the learning rate to 0.5, and again, sorry, um, I've been playing around with this, and like the comment here says, originally I had set it to 0.001, but I found good results at 0.5. So I'm going to do this run with 0.5, but I'm still trying to fine tune this into seeing where I get my best results, and I'll do both the runs, right? So I'll do a run with 0.5 and I'll do a run with 0.001 as well. And then I'm basically setting how many features are there. So again, it's going to be 11, because the x train is basically a tensor, and its shape is 11. Number of classifications is 2, because we've set up a 2 by 2 matrix, and setting the number of epochs, and the number of epochs by 10 is what I'll use here, so that every 10 runs you'll basically see an output being printed for model training, or for what our error rate is. And then in the hidden layer I basically have 10 neurons right now. And again, I was playing with this, and I tried with 20 neurons, I've tried with 10 neurons, and I found that 10 neurons gives me a close enough output to 20 neurons. So I've basically set it at 10 right now, but I do a run with both, right? Then what we have here is the input tensor and the output tensor, and these are both placeholders basically. So and what they're going to do is they're placeholders, both holding floats, and their shape is going to be number of features. So 11 here and 2 here, right? And the reason why I've done it this way is you could later change it if your data changes. A few functions. So basically I'm creating a batch, and we have data which is 1599 rows. So I'm basically going to create batches for them. This is my first layer. So I have two possibilities. You could run this as a single layer model, you could run it as a 2-layer model. So this is my hidden layer, and this is my output layer in case of a 2-layer model, and in case of a single layer model, you'll see here I've basically just handled it that way. I'm using the gradient descent optimizer. I did want to try a few more optimizers, but I think I've run out of time. So at this point, I'm going to stick with gradient descent optimizer, because that's what we've learned in our theory, and I will continue to work on this. And then I have a function that calculates the loss, and it's using again a TensorFlow library called reduce sum to calculate loss based on whatever is the output tensor versus whatever is the actual output and batch size. And then I'm also have a function to calculate accuracy, and that is again on reduced mean, and it depends on what is the actual output versus what is in the y tensor, or whatever is the actual output here versus what's the defined output. So in order to run the model, basically why I did this, why I extracted this out a little differently, is because I'm in the same program. I basically have single layer and multi-layer, and I wanted to do different things in them, so I extracted the run model out. And this is basically the same thing. So it will initiate a session, it will initiate all global variables and initialize them, and then it will set, sum of loss to 0. And then for I in range epochs, which is, I think I set it to 1,000. So until you have for I goes to 1,000, basically we make a batch, and then we feed the dictionary with input placeholders, and we basically run we run the epochs for I, and for every 100 runs we basically print whatever is the average loss and the sum of loss, right? So, and we set the sum of loss back to 0. So what we are basically doing here is, after this is done, we basically print that the model fitting is complete, and then we print the final accuracy, which is coming from the sum of losses. So what we do in the single layer is, when we are running this as a single layer, we have only one layer here. So we are basically running it as output, and the output is basically getting the input placeholder and the number of qualifications, and that's it, right? But when you are running it as a multiple layer, we are using the ReLU function, and again we are passing number of input placeholders and number of output neurons, which in this case would be 10. And then in the next output layer, we are basically passing the ReLU here, and we are also passing the number of classifications. So this, I'm sorry, one sec. So this ReLU is actually TF scope. Yep. So the hidden layer is actually defined here, and as you can see, it's basically using the softmax function for ReLU. And then once this is done, it basically prints the calculates, it calculates the scope, calculates the it does the training, it calculates the accuracy, calculates the loss, and then it will basically run the model, and run model will basically print out whatever is required, right? So let me show you a run of this wine test TF. So right now we are running with normalized data. Our learning rate is 0.5 and the number of hidden neurons is 10. So if I run this right now, it should start printing in a second. There you go. So as you can see, it basically printed that it's running with the normalized data. It printed the number of the column headings for the features and what it is using for quality label. And then these are, the average losses after every epoch. So loss is pretty low typically, but the accuracy is 76.58, and this is while we were running the multi-layer model. And for the single layer model, it's even lower, which is 72.97. So if I change this to say 20 neurons now, so you see the accuracy in the single layer one went up, but in the multi-layer it actually came down a point. So it's kind of a hit and miss typically. I mean, it's still above, like the multi-layer model is still above 70%. And now again, I did another row and the accuracy came down to 72. So I didn't find a lot of benefit of having additional 10 neurons in the hidden layer for this data that we are looking at, and that's why I set it to 10 on the previous run. So if I set it to 10 again here, you'll see we get down into the same ballpark, not a pretty big jump from where we want to be, right? It's still 73 and 73. Now if I change my learning rate to 001, let's see how that behaves. Yeah, so my accuracy actually dropped down significantly when I changed my learning rate to 0.001. So let me do another run. And this is the lowest I've actually seen it. I've never seen it come below like 70%. But yeah, so see here you'll see it's back up at 72. So I didn't find a lot of benefit of having the learning rate so low and going through the process. I actually fine tuned it at 0.5 is basically where I found it to be, always above 72%. Now, if I run the same model with unprocessed data though, so again, this is probably first time running it with that learning rate, but let's see what we find. So the only difference is now that we are running with unprocessed data, it's not going to run any processed data, so it will not actually run this loop. So it will take the unprocessed data and go from there, and you can see like the accuracy I'm getting at unprocessed data is like phenomenal. So maybe we didn't need to process this data at all, but the accuracy that I'm getting here is definitely much better. It's actually just 100% accurate as compared to what we were. So this is at learning rate 0.001. If I actually go ahead and set this to 0.5, you will find that again the accuracy doesn't change a lot. It's still in the same range. So again, I left it at that. Although when you set the learning rate so high in your single layer model, your average loss actually becomes NaN. So again, something that I was looking into why that happens and how. But even if you set this to 0.001, you're not going to get any better accuracy than close to 100%, right? So where we are is good enough, and that's why for this term project and for the data that I had at hand, I definitely think that running this neural network without pre-processed data is the way to go. But I am honestly looking into why that is the case and why having unpreprocessed data is helping us move the accuracy needle almost 30 points in some cases, if not at least 25 points in the positive direction, which is a pretty significant difference, right? I mean, you're going from 75% accuracy to 100% or approximately 100% accuracy, and that's a pretty big difference. So that's something that I'm trying to dig into now, and I'll continue to dig into even if the course is over, as to what are the factors that actually address that, right? And again, we could run the same model by changing the number of hidden neurons to 20, again unpreprocessed data, and the program is written in such a way that it should just work. So again, not a big difference when you have 20 neurons versus 10, and that's the reason why, although originally I was thinking of 20 neurons, I brought it down to 10, because why waste resources if you don't need them? Because eventually the number of neurons, as they go up, your computations are going to go up, and it's going to be eventually comes down to resources. So if you are getting the same output from less number of neurons, and I've not gone below 10, but if I'm getting a good enough output from 10, I think I'm happy. So that's what I had for my neural network. Again, the code is uploaded to GitLabs and GitHub, and if you ever need to download that, feel free. But this is what I have, and I think this is a neural network that gets me the solution to the problem that I had in mind. Thank you.